Okay, so in the last video, we established the idea of convection in the atmosphere. We said that warmer air is less dense than colder air, and so it exerts less pressure. It tends to rise relative to colder air, and colder air tends to force its way into warmer air systems. And if we consider that with respect to the temperature of the Earth's surface, as it results from the energy we receive from the sun, the flux of energy we receive from the sun, the temperature of the Earth's surface causes the air to be different temperatures. It emits infrared radiation, warms the air, the greenhouse gases specifically. Those are at different temperatures across the Earth's surface, and that causes air to circulate. Cooler air at high latitudes pushes towards warmer air at low latitudes. And so if we weren't on a rotating sphere subject to the Coriolis effect, we would have this kind of idealized circulation pattern. Instead, because of the Coriolis effect, we don't. It actually breaks down, and it breaks down into these three individual convection cells in the northern hemisphere and three in the southern hemisphere. And so if we look at the slide for that, this cartoon down in the bottom right shows three convection cells in the north circulating in the ways indicated here, right? And those are indicated by the black arrows over to the left. Okay, and so if we consider how the surface currents look there, they would, if we drew those on here, they would look something like this, right? They're going from 30 degrees north and 30 degrees south towards the equator, and from 30 north and 30 south up towards 60, okay? They're going in opposite directions. That gives rise to the idea of convergence and divergence. The intertropical convergence zone is centered at the equator. Roughly, it actually migrates north and south throughout the year because the Earth's axis has a tilt, but that's a concept we get to later. But so those are the surface winds without the Coriolis effect. But as we learned, because we live on a rotating sphere and different points on the Earth's surface are moving at a different rotational velocity, right, or tangential velocity more specifically. They're all rotating one full rotation every 24 hours, but different points move a different distance in that amount of time, and consequently they're moving at different velocities. That was shown by this graph in the bottom right. This is the tangential speed of Earth's surface, and at the equator it's something like 1,000 miles an hour. At the poles it's 0. They're just turning in place, rotating, right? But if we think about that in terms of a particle moving across Earth's surface, like the wind, if it's moving at the same speed as the surface below it, okay, and that's shown in the bottom right here by this figure. The connection is getting kind of bad on this iPad. That's shown down at the bottom right. If a particle is moving from point A down there to point B over time, right, over that same amount of time, the time it takes for it to get from point A up to this latitude where B exists, the Earth rotates. That particle is moving at this speed of A, to the east along with it. And over that course of that amount of time, A moves to A prime, and B moves to B prime, okay? But that particle left A moving northward, but also moving eastward. And so when it arrives at the latitude of B, it actually misses B. It goes out here to the right, okay? And so if you're standing at B watching this take place, or if you're standing out in outer space watching it, it appears as though that particle bends to the right. It's actually traveling in a straight line through space, but it looks like it bends, its path bends, because from the frame of reference of B or A, right, it moves off course. Okay, there's a lot of videos on YouTube and animations that make this a little bit more clear. If it doesn't make a whole lot of sense, check one of those out and you can see how a ball moves being tossed across a merry-go-round from different perspectives. That could help make sense out of it. But it's enough to just accept that this exists if it doesn't make 100% sense. But it certainly does, and it affects the motion of a particle traveling across Earth's surface, like the wind. Okay, and so rather than these straight lines like are indicated on the iPad, they bend. Okay, in the northern hemisphere they bend to the right, of their expected path, and in the southern hemisphere, they bend to the left of their expected path. Okay, and that gives rise, it's really responsible for the breakdown of a single convection cell into 3 individual ones, but it also gives rise to the dominant winds we experience at the Earth's surface. We have the trade winds that are just north and south of the equator, and we have the westerlies that are at about 45 degrees north and south. There would be westerlies down here in the southern hemisphere as well. And those are shown on the iPad here. You know, the trade winds are somewhere in this area, blowing this direction, and the westerlies are somewhere up here, blowing in that direction. Right? The westerlies in North America we call the jet stream, but that current circles the globe and affects climate and weather patterns on all continents. And so warmer air exerts less pressure than colder air because it's less dense. That causes circulation. A more dense substance will want to be either below a less dense substance or just push it out of the way and move in to its area. And so that drives circulation, right? Cooler air moves towards warmer air, and warmer air moves up relative to colder air. That circulation, but how does this affect precipitation and water vapor? That's the next step of this discussion, and we'll save that for the next video. But you know, it all comes down to the fact that warmer air can hold more moisture than colder air. Okay, and so warmer air is less dense and can hold more moisture. Those are the two key components of this.